Well, good morning, everybody. Dr. Heldman here. Happy springtime. In this video, I want to go down the road some more with Linux cluster computing. What we want to do is we want to supply a little bit more difficult C program for the cluster to use to see how it's performing. In fact, what I'd like to do is I'd like to have a program that tests with just one node, master node, and then does the same thing with all three to see if we're getting better performance out of the cluster than we would be out of one machine. So let's get started. It should be important. The code's a little bit difficult. It's not bad, but it shouldn't be too bad for you, and I'll explain it as we go along. Let's get started. All right, so on the screen you can see that I'm on master node, which is where all the action happens for the code. I've called this cluster perf.c. So what this is doing is estimating the ability of the cluster to perform compared to a single node. So in this case, we're going to use master node to run through a calculation, and then we're going to do another calculation using all of the nodes to see how they compare. And the idea is that we're going to check the number, we're going to calculate the value of pi out to a fairly large number of characters just to see how we do. And in order to do that, we're going to use a little bit of calculus. Now this is where, if you've never had calculus, it's fine. Calculus is fun. I've been through it. I'm terrible at math. I'm not very good at it. I've had several years of calculus, but I want to show this integral to you so you can see what it looks like. So here's what we're dealing with. We're dealing with a thing called a Riemann sum. Here it is spelled out for you up here. And this is a calculus equation. Essentially what we're doing is we're saying that the value of pi, this is the symbol for pi, which I'm sure you're familiar with. These squiggly equal signs, this means approximately equal to. So pi is approximately equal to 4 times, and then this little squiggly symbol here is called the integral. We're doing what's called integration, and we're just going to chop things up into very, very tiny little rectangles and sum them all up. And that's how we're going to get the accuracy out of things. This is used quite extensively in engineering technologies, things like that. So we're going to integrate from 0 to 1, and then for every pass through this integration, it's a little bit similar in idea to a for loop. We're going to run this equation here. So that's what the thing looks like. Then the dx on the end is always put there to illustrate that I'm bashing this, I'm not getting this correct, but the idea is that dx is always going to show up there as a part of the calculus equation. So let's take a look at the code here. So we have a bunch of includes. You remember that we're going to path in our area, the place where we can find mpi.h. We're also going to include standard.io.h, the standard library.h, the math library, and the time library. Now don't worry about having to copy this code off of the screen. What I will do is I will take a copy of this and paste it below in the show notes so that you have all this code so that you can apply it as well. This is saying that the number of steps we have is going to be 1 billion. This number is 1 billion here. And when you see define, what you're doing here is we're seeing that we're declaring a constant called num steps. This is pretty common when you're a C or a C++ programmer and you want to declare a constant. Typically you're going to declare this in uppercase here. So what we're doing is we're just defining a value called num steps, and we're setting it equal to 1 billion. Now you can see where they've integrated this equation. This is the integral equation right here from 0 to 1. And we've got some functions here. Now let's take apart these functions because this is where we're going to get into the mode of what's going on here. So first of all, we're going to compute pi in serial, and what we mean by that is we're going to have master node just do the computation. We declare a variable called step, and this time it is of type double. There are 2 floating point decimal types that you can select, and you can select float, which is a smaller number than a double, And Microsoft Visual Studio for many, many years now has just defaulted to a double. Why? Well, because it can hold a lot bigger numbers, and that's just the way it is, I guess. I don't have a real technical explanation for that. But just be aware that when you're working with Microsoft Visual Studio products, it's going to want to use a double as opposed to a float. So we're declaring a double here. And the double has a percent sign, or a dot for the decimal, and then a 0. So this is properly declared here. We're saying that we have a double step, and we're going to call it 1. And it's going to be equal to double num steps. Now what are we doing here? Well, when we originally declared this thing, it's going as an integer, which you can see on the screen there. If I point to it, IntelliSense tells me that num steps is currently an integer. Why? Because we didn't put the decimal point on the end of it. Here what we're doing is we're doing a process called casting it. So we're going to take num steps and turn it from an integer into a double so that we can use it in our equation. Then we declare a double called sum, and we initialize it to the number 0, and we go through a for loop. So for int I get 0. Now you remember this is very common C stuff. So when we have a for loop here, it's 3 components. The first component is where we're declaring the counter, and in this case we're going to call it I, and we're going to initialize it to 0. Then we're going to go as long as this section here says how long are we going to stay in this for loop. And we're going to stay in there as long as I is less than num steps. And then we're going to increment the counter after each pass of the for loop. Then we just go ahead and apply this nomenclature here. We declare a variable called x. We set it equal to I plus 0.5 times step, which is right here. And then here we do the actual calculus equation. 4o, sum is going to be plus equals, meaning that whatever's currently in there, we're going to add to it. So on first blush, when we do the first sum, we just put a number in there, but after that, we add on to the number that's currently in sum. And then this is just the integral equation right here. We've just taken what we had in our picture, or up here, and we've mapped it into the integral equation. Now there is a way in the C math libraries to do this exponent here, x raised to the 2, but it's just as easy to do x times x. Remember your order of operations here, because this could get pretty dicey if you did not include those. Parentheses are the top of the order of operations. So here we've got this right here, those parentheses. That's where the program is going to go first. It's going to do this math here, 1.0 plus, but before it does that, it's going to take x times x, because x times x is in the next order of operations. And then it will add 1 to it, then it will do the divide, and that's how we wind up with that number. So in this case, order of operations is very, very important. So I'm going to put order of mathematical operations is very, very important. Sorry, I'm not typing well. Need to be really super aware of that, and I'm sure you remember that from your wonderful math classes in your school. And then we return step, this times the sum. And so that's how the equation's working. Then we do a compute parallel. It's basically the same thing, but what we're doing here is we're grabbing the rank and the size as well as the num steps. I should have pointed out to you that these are arguments, so we're going to pass in the number of steps that we want to take to compute pi serial, and this whole thing here is a function, which means that we have to call it somewhere. In our program, what we're going to do is we're going to make a call to compute pi serial. We're going to pass in the number of steps that it gets, and then we want it to execute those and return some number back to us. Here's the same thing for pi parallel. Now this is also a function here. It's a little bit larger function because we're including MPI stuff in here, like the rank and the size. We do the same thing. We've got a double step. We've got a local sum. We go through the for loop here. It's the same idea. Then we declare a double global sum, and we do the MPI reduce. So what we're doing is we're casting everything into a double, given all of the nodes, and then we're going to return step times global sum. Now I talked about MPI reduce in a different movie, so I'm trusting that you know what that means. The ampersand is going to go into the place where we're holding this variable and get the data. We're going to return a double. We're going to return the sum of those things through our COM world. So this is all nodes participating and doing the same calculation as we did, and we're calling it parallel as opposed to serial. Now you remember that when we're working with C program, we always have a main function. Main's always the first place we go. For the most part, you can ignore this right now. This isn't something you need to be seriously worried about with this argc, char star argv. All it's really saying is, hey, we might have the ability to start this program with some arguments. We're not going to, but it is possible that we do, and so we're going to leave that there, and we're going to return an int to the calling program. In this case, it's us executing the program from the command line. We declare a rank and a size. We declare pi serial as 0, pi parallel as 0. These are doubles. We declare a start time and an end time. This is where this standard lib comes in. That's what's keeping the time for us. And then we've got the standard stuff. So we've got MPI initialization. We get the rank of the clusters. We get the size of the clusters. And then we print out some material here that tells you how long this thing is going to take and what we get. So it's going to tell you running MPI computation using %d steps, num steps. It's going to print that out. And then there's a couple of interesting things here. So we have this MPIW time. This is a function that stands for world time. And the reason we're doing that is we are converting it to the cluster's time system rather than the computer's time system. So that's an important feature here. What we're seeing is we want to work based upon, we've got these 3 nodes that are all participating together, and we want to work on their time frame, not the local computer's time frame. So that's why we're invoking W time here. So start time gets MPI W time, the time when the clusters start doing their work, and end time gets W time as well. And then finally, the output is rendered in, this is 15 decimals of float and 6 decimals worth of seconds. So we're just showing you how long it took to do these things. MPI barrier is simply making sure that all the nodes start at once. And that's it. There's not a whole lot to this thing. We're saying that start time is MPIW time, and then pi parallel is going to be compute parallel. This is where we're calling it. We're calling compute pi parallel function, passing in num steps, rank, and size. And then we have end time here. If rank is equal to 0, we print this out, we finalize, and we return. So that's the nature of the code. It's not ultra complicated. Like if you stare at this a while, and you know, maybe even take a 3-ring binder out and try and draw it out on paper. I always used to advise my students to think about how things were happening on a tablet. Like you could draw this out with paper and pencil. It might help you understand the logic behind this. It's not a heck of a lot of code. What is it? It's about 70 lines of code. So it looks fine. Everything's fine here. Now what we want to do is we want to run this thing. So I can get rid of hello MPIC and launch JSON. I don't care about those right now. I'll just have this appearing here. And I'm going to go ahead and select run without debugging. Now what this does is this runs a code, make sure that it looks okay, and we'll see what we come up with here in just a second. Very good. Okay, we're all done. Now we talked about this in the previous movie. If I go to output, there's nothing under output. If I go to debug console, I can see that this ended with exit code 0, which is exactly what we're looking for. That means that it actually did run. Go back to terminal, and you'll notice here that cluster performance right here now is an executable. The next thing that we would want to do, now that we know that we've successfully run that, is we do a secure copy. So I'm going to secure copy cluster underscore performance to bill at, and I'm going to do compute node 1 first, colon, tilde slash documents slash MPI projects. So I'm going to copy this over to the MPI projects field. There we go. That looks really good. I'll hit my up arrow, and I will tell it that I want to copy it to cluster node 2 as well, and hit enter. Very, very good. That looks really good. And now let's give it a try. We're going to go ahead and try running this. So it's MPI run, and then we do a tac host file. It is going to be MPI tac hosts. We check and make sure that they're still up here. Here's MPI host, so that's great that that's sitting right there. And then what we do is we tell it that the number of processes we want to use are 6, and we'll do ./MPI, excuse me, it's not MPI benchmark, it's cluster underscore perf, like so. And we just run this thing and see how it does. So this is printing out what it's doing. It takes it a minute to run, but it's not super long, actually pretty fast. And if you take a look at the results, here's what it's telling you. So this is very, very cool that this code works this way, because you immediately get the idea of what's happening here. So when we're in serial mode, meaning master node did all of the calculations all its own, this is the number that it came up with for pi, and it's 15 characters in length. And then it said that it took 2.817029 seconds, and of course it's using W time, which is, we could call that wall time. It's not using the CPU clock, it's using its own clock to do this work. Now when we run 6 processes in parallel, we come up with this number here, and take a look at the difference in the numbers. So here we get to 358, okay, but then we wind up with 9971. We get to 358 here, which is great. Those two match, but then we get to 9705, which is a little bit smaller number. And then it only took 0.5 seconds for it to calculate versus nearly 3 seconds for it to calculate. Now you might have other questions about that. Well, which number is more accurate? My guess would be that since we're allowing it to run in parallel with the 6 processes, that is the better number for pi. You'd have to actually run this out and have it, you could go even research this and see what it tells you. But the point here isn't necessarily the accuracy of the numbers. If I was doing this for the space station, I'd want to make sure that the calculations were absolutely correct. But the point that I'm trying to make here is we're trying to show that when we're running something in serial mode, like we are running it in master node here, it's going to be completely different and take a little bit longer to run than if we run it in parallel with all 3 of the nodes running, and it gets us a little more accurate number, and it took a lot less time to do so. So this is really, really good proof about how Linux cluster computing works. And if you imagine expanding this thing out to 1,000, 10,000, 30,000, whatever, 100,000 nodes, and getting it to do these kinds of calculations, you could see how it would be very, very useful in terms of crunching really, really large processes and calculations. I hope you enjoyed this movie. Please subscribe and like it, and tell your friends about it. I'm trying to build the channel, and you're welcome to leave comments on this. I'm happy to answer any comments that you might leave. And thank you. Have a great day, and I'll talk to you in the next video. Bye-bye.